Okay, good morning, everyone, or good evening, good afternoon, depending on where you are. Welcome to the SNAPP seminar. It's our great pleasure to have Gardner from Amherst College speaking today. Christy is an assistant professor in computer science department at Amherst College. That's also her alma mater. Her work primarily focuses on designing and analyzing dispatching policies for large-scale systems. I've read her very interesting and impressive work about queues with redundancy scheduling. She did her PhD and she received her master and PhD degree, all from Carnegie Mellon University. And today she will present a general power of D dispatching framework for heterogeneous systems. The floor is yours, Christy.
All right, thanks so much for the introduction, and thanks to all of the organizers for inviting me to speak today. So the work that I'm going to talk about today is based on joint work with Jazim Abdul-Jalil, Sherwin Durruti, and Alexander Wickham. They're all at the University of Minnesota. And this talk is kind of about some of our recent work and some of our ongoing work in the space of dispatching in heterogeneous systems. So I want to start with a very general question, which is how to dispatch in multi-server systems. So this is a very classical problem in queuing. We might have multiple servers. In this case, we have 2 servers. We have a job that arrives to the system, to a dispatcher, and the dispatcher has to make a decision about where to send this arriving job. So a very well-known, very classical policy in this space is join the shortest queue. The idea here is that the dispatcher is going to ask both of the servers how many jobs are in your queue. It'll get back a response of 1 from the server on the left. It'll get back a response of 3 from the server on the right. And because 1 is less than 3, the dispatcher is going to send this job over to our server on the left. And JSQ works very, very well. It's known to be optimal in certain settings. But when we think about modern computer systems in particular, this setting where we have just 2 servers is not very realistic anymore. So instead of thinking about multi-server systems where we have only a really small number of jobs, we want to move to thinking about large-scale multi-server systems where we might have hundreds or thousands of servers. And in this setting, the dispatcher can no longer ask every server for its queue length when a job arrives. We still have to make the same choice of where to send the job, but the communication cost is simply too high to get queue length information from every server. And so instead, what the dispatcher might do is what we call this kind of power of D policy. One policy that falls into this power of D category is join the shortest queue among D, JSQD. The idea here is that instead of communicating with all of the servers for their queue length information, our dispatcher is just going to choose some number of servers, D, and in this case, D is equal to 2. The dispatcher will ask just 2 servers chosen at random for their queue length information, and will send the job to the shorter queue among those queried servers. And this is nice. This works very well. One of the really key results in this space is that using D is equal to 2 is enough to get most of the benefit of the full join the shortest queue policy, even though we're using only a very small number of queries here. But again, we want to think about, what's going on in today's systems, what might be a slightly more realistic, more interesting setting. And what we might come to is that our servers are not all the same. So instead of dealing with a homogeneous system where all of our servers are exactly the same, it doesn't matter where we send a job, we're dealing with a heterogeneous system. And for the purposes of this talk, we're going to think about heterogeneity in terms of the server's speed. So what I've drawn here on my servers, I've used different colors to represent different server speeds. We have some green servers, which are very fast, some yellow servers, which are kind of medium speed, and some red servers, which might be slower. And now we can imagine implementing a policy like JSQD. There's nothing preventing the dispatcher from executing this policy. But we want to ask ourselves whether this is still a good idea once our servers are not all the same. So to think about this question of whether policies like JSQD are still a good idea in the heterogeneous setting, I want to look at some numerical results, and we're going to look at our mean response time as a function of lambda. This is going to be simulation results for a particular system setting where we have 300 fast servers and 700 slow servers. The first line that I'm going to put up here is random dispatching. I just send the job to some server that I choose uniformly at random. And I'm putting this up here mostly to show what a bad choice of a policy looks like in terms of response time. Once we start looking at our JSQD policies, JSQ2, using sampling just 2 servers, does much, much better than random. And as we continue to increase D, we do better and better, all the way down to just our regular old JSQ. This is our not so feasible to implement policy, where we're looking at the queue lengths of all of the servers. And so at face value, it kind of looks like, yeah, in heterogeneous systems, we're doing pretty well. JSQD is doing a pretty good job of achieving low mean response time. But I want to put one more line on this graph. This last line that I'm going to put here is a theoretical lower bound. Where we arrive at this theoretical lower bound is that by imagining that we have a system where all of our servers are fast. So instead of having 700 slow servers, we're just going to have 1,000 fast servers that are all running at this fast rate. And we're going to run JSQ among all of our servers in this fast system. So this is not a lower bound that actually ought to be achievable in the real system that we're simulating here, right? We've made some of our servers faster. We've just increased the capacity of the system. But at low lambda, at very, very, very low load, we should actually be able to meet this lower bound. Because when load is very low, we should be able to get away with only using our fast servers. And our fast servers, we really should be able to find idle fast servers all the time. So there's a gap, there's a pretty noticeable, pretty substantial gap between what all of these policies, all of these JSQ-based policies are achieving in heterogeneous systems and what we think should be possible. So we want to revisit this question now of what should we be doing in large-scale heterogeneous systems? And a natural alternative to JSQD is shortest expected delay among D. Now, after querying our D servers, instead of asking which server has the fewest jobs, we're going to ask where will the new job wait for the least amount of time. So we're going to take our queue lengths and scale that by the speed of the server. So we're going to sample our D servers. And in fact, in this case, we might decide that we would rather send the job to a faster server with more jobs in its queue rather than a slow server with fewer jobs in its queue, because the expected waiting time at the fast server is still lower. So let's return to our numerical results and look at what SED achieves for us. We can see that using SED4, we actually are reaching our theoretical lower bound when lambda is very, very low. But there's still something to be gained. Maybe we can do a little bit better when lambda is high. And so our goal here is to explore what is possible in this space. Can we do better than SED? Can we come up with better ways of leveraging server heterogeneity? Now, I want to point out that SED uses server speed information in a particular way when it's making decisions. SED uses that server speed information after D servers have been queried to decide where among those queried servers to send the job. There are other policies in the literature that also use server speed information when making dispatching decisions. Another policy, for example, is balanced routing. Balanced routing is a power of D type of policy, but instead of querying servers uniformly at random, under balanced routing, we query servers in proportion to their speeds, so that a fast server is more likely to be included in the D queried servers than a slow server. And so what's interesting to me about thinking about SED versus balanced routing is that SED and balanced routing are using server speed information in very different ways. And this brings us to our key observation that our dispatching framework will be based on. That observation is that there are 2 points at which the dispatcher can use server speed information. The first of those points is in the querying rule, which answers the question, which D servers should we query? And this is the point at which balanced routing is using server speed information. The second point where we can use our server speed information is in the assignment rule. The assignment rule answers the question, after we've queried our D servers, where should we send the job? This is the point at which SED is using our server speed information. Now, most policies, most heterogeneity-aware policies in the literature tend to use server speed information at only one of these decision points. And so our idea here is to explicitly decouple a dispatching policy into a querying rule and an assignment rule, and to use server speed information at both of these points to try to find the best overall policy that makes the best use of server speed information in the combined querying and assignment decisions. So I want to talk a little bit about the system model that we're dealing with, and then we'll come back and think about what we mean by querying rules, what we mean by assignment rules. So we're going to make some modeling assumptions. We're going to think about systems with K servers and S server speed classes. So my little example here, I have 3 server speed classes. I have KI servers in each class I. Our service times are going to be independent, and they're going to follow some general distribution G sub I with mean 1 over mu sub I. And this distribution is going to have the same shape at all of the servers, meaning that we're sort of following the distribution, just scaled differently at different servers depending on the mean. Our server classes are ordered so that class 1 is the fastest class of servers and class S is the slowest class. Jobs are going to arrive to the system as a Poisson process with rate K lambda. So our arrival rate is scaling linearly in proportion to the number of servers in the system. And the dispatcher has to decide immediately to which server to send an arriving job. At our servers, we are allowed to use any work-conserving scheduling policy. The numerical results that I'll show you in this talk will assume first come, first serve scheduling, but the analysis that we do in our system allows for any possible work-conserving policy. So within this space, with these assumptions, our goal is to design dispatching policies that achieve low mean response time. And again, our key idea is that a dispatching policy can be decomposed into a querying rule plus an assignment rule. So I want to take a little bit of time now to explore what possible querying rules look like and what possible assignment rules look like. And then we'll come back and think about dispatching policies as a whole. So our querying rules, we're going to need a little bit of additional notation to describe our space of querying rules. We're going to let lowercase d denote the number of servers that we query. This is a constant, and we're going to consider d's that are much less than our number of servers k. D sub I is going to denote the number of class I servers that we query. And D vector will hold on to all of our DIs, and this is what we call the query mix, the number of servers of each class included in a particular query. And then finally, I'll use this script D to denote the set of possible query mixes. We are going to consider querying rules that satisfy 2 important properties. The first of these properties is that our querying rules are symmetric. This means that servers of the same class are treated ex ante identically. We can't keep track of any additional information like a server's index or something about the server's properties. If we have 2 servers that are both of the fastest server class, we have to treat them identically when we are querying. Our second property is that our querying rules are static, and this means that our dispatcher does not maintain any history. When we're making querying decisions, we're not allowed to know, for example, what set of servers did we query when the previous job arrived, or where did we send the last 5 jobs? We have to make each decision independently of the history of the system. So once we have these 2 properties, really what a querying rule comes down to is a probability distribution over the set of possible query mixes. And every time a job arrives to the system, we draw a query mix from this distribution. So let's think about an example of a querying rule. We're going to think about a system where we have S equals 3 classes of servers, and we're going to query D equals 4 servers. And our querying rule says the probability of querying query mix 220 is a half, and the probability of query mix 121 is a half. So what this means is that when a job arrives, With probability at half, we have this mix 2-2-0. We're querying 2 servers from the fastest class, 2 servers from the middle class, and 0 servers from our slowest class. And with probability 1/2, we have mix 1-2-1. So we're querying 1 server from the fastest class, 2 servers from the middle class, and 1 server from the slowest class. Our symmetry property means that within the slowest class, we are equally likely to choose any of the servers in that class to be the 1 server from that class that's included in our query. So this is one specific querying rule, but a lot of our work is about trying to find the best possible querying rules. This turns into an optimization problem, so I want to talk about the entire space of querying rules that we're ultimately going to optimize over. So our broadest set of querying rules is called gen. This stands for general. Any general distribution over our set of query mixes is allowed here. This is any query rule that follows our static and symmetric kinds of properties. Within gen, we have many subfamilies of querying rules that restrict the kinds of distributions over our query mixes that we're allowed to consider. So our IND class says that each of the D queried server classes is chosen independently. Every time we're going to choose one of our D servers, we roll a die, and we might roll a different die, different numbers on the sides of the die for different servers in our query. Within IND, we have the IID query rule family. In IID, again, we're choosing each of our D queried server classes independently, but from the same distribution for each server that we query. A different subset of IND is the family that we call DET for deterministic. This says the same query mix is always used. I'm, for example, always going to query according to mix 1-2-1. Every time a job arrives, I use mix 1-2-1. Another possible family is SRC. SRC stands for single random class. And the idea here is that every time a job arrives, we probabilistically choose one of the server classes and then query all D servers from within that class. And our last family lies in the intersection of a number of these earlier classes. And this is single fixed class, which says I'm going to choose at the beginning of my system's lifetime a single server class. And I'm always going to query servers from within that class. This is effectively throwing away all but one of our server classes so that we end up with a homogeneous system with fewer servers. Not necessarily a sensible thing to do, but a possible thing to do. Now, everything that I've got up on the screen so far are querying rule families in the sense that there are still parameters that control different policies that exist within those families. Single fixed class is parameterized by the class that I'm going to choose. IID is parameterized by the die that I'm going to roll, the probability distribution over the classes for each server. And there are a few specific policies of interest that use a specific parameterization. One of those policies is uniform. The uniform querying rule chooses every server with equal probability. This is the querying rule that's used with policies like JSQD or SEDD. There's also what we will call the balanced routing querying rule. This is the querying rule used by balanced routing, where the probability that a server is chosen to be a part of the query is proportional to the server's speed. All right, so given our space of querying rules, our goal is going to be to choose a good querying rule, choose a parameterization that yields low mean response time. The second part of our dispatching policy then consists of our assignment rule. So again, we're going to need a little bit of notation to think about different possible assignment rules. Our D vector again tells us our query mix, and our script D tells us the set of possible query mixes. Once we query our servers, we're going to get some additional information. And I'm going to encode that additional information in this X vector. Now, I'm being a little bit vague about precisely what the X vector encodes because this will depend on the outcome of our querying rule. We might, for example, ask the servers how many jobs are in your queue. We might ask the servers how much work is in your queue. We might ask the servers, are you busy or are you idle? So our X vector is just going to encode whatever information we get back from that query, depending on what we ask our servers. And our script X is going to denote the set of possible query results. Just like our querying rules, our assignment rules are going to satisfy two properties. They will be symmetric and they will be static. And these are the same two properties that we were dealing with in our querying rules. We are not allowed to treat servers with the same state differently. So if we have two servers that are of the same class and provide the dispatcher with the same information in the query result, we have to treat those servers identically in the assignment decision. And our assignment rules have to be static. We're not allowed to make assignment rules holding on to any history about what happened in past queries or in past assignment decisions. So again, just like our querying rules, our assignment rules are going to be probabilistic, where what we'll do is we'll take the information about what set of servers we queried, we'll take the information that we got from querying those servers, and then we will probabilistically assign the job to some server based on that information. So I want to go through an example of an assignment rule, and then we'll talk about the full space of possible assignment rules. So we might imagine, going back to our querying example, that we have queried mix 1 to 1, one fast server, two medium speed servers, and one slow server. And now maybe our query asked the servers, how many idle servers are there? They asked each server, are you idle or are you busy? And so maybe our servers responded as follows. Our green server is busy. Of our two yellow servers, one is idle and one is busy, and our red server in the query is idle. This would correspond to an X vector of 0, 1, 1. This vector tells us how many idle servers are there in each class in the query. So now, what do we do with this information? Well, based on the query mix that we've queried and based on the information that we got back about the idle status of the servers, we are probabilistically going to assign the job to one of the servers. And these alphas represent the probability with which we assign the job to each possible server. Now, I want to make a couple of observations about this probabilistic assignment. And the idea here is that we're going to be able to do a little bit of pruning to get rid of nonsensible assignment decisions. The first observation is that within the same class of servers, an idle server is always preferable to a busy server. So I have these two servers in the middle speed server class. These are the yellow servers in my picture. One of them is idle, one of them is busy. Our job is going to be happier. Our job is going to be better off if we send it to the idle server rather than the busy server. And so I can just eliminate this busy server from my set of servers that I am considering entirely. I have an option that I know is going to be better. My second observation is that a faster idle server is always preferable to a slower idle server. So I have an idle medium speed server and an idle slow server in this picture. Our job is going to be happier if we send it to the faster idle server. And so in this example, I can eliminate this slow idle server from consideration. What we end up with is that among our queried servers, we are always going to want to choose to send our job to either one of the fastest idle servers or to a busy server that's faster than the fastest idle server. And that's in fact the set of servers that we've ended up with after pruning this example. So what we'll do is we'll set our probabilities to 0 on these servers that we've eliminated, and we'll adjust our probabilities on the other servers. And this kind of pruning just lets us reduce the space of assignment rules that we are considering so that we're only actually thinking about assignment rules that do reasonable things. We've eliminated poor choices from consideration. So I want to talk about the space of possible assignment rules. And again, our assignment rules are all parameterized by these alphas that probabilistically assign our job among the queried servers. So the largest assignment rule family that we consider is what we call CLD. CLD stands for class and length differentiated. And policies within this family can use both server class, server speed information, and queue length information when making assignment decisions. Within the CLD class, we have a smaller class called CID. CID stands for class and idleness differentiated, and rules within this family can use both server speed information and idle busy status. So the example that we just walked through was an example of a CID policy. We knew whether our servers were idle or busy. We knew what class they were, but we didn't know how many jobs were in the queues of the busy servers. A different subset of the CLD family is the LD family, length differentiated. Policies within the LD family can use only queue length information, but not server speed information. In the intersection of these two, we have the ID, idleness differentiated family, and these are rules that only use idleness information. They don't have more detailed queue length information, and they don't have server speed information. And finally, the CD, class differentiated family, can only use class information. They're not using any information about whether the servers are busy or idle, how many jobs are in the queue. They just know what speed the different servers in the query are. Now, we also have a few specific assignment rules that are of particular interest. And these are rules that are sort of pre-parameterized. They don't have any flexibility in the probabilities that we are using. One of these policies is JSQ. This is a length differentiated policy, but it's not a class and length differentiated policy. We're just looking at the number of jobs in each queue and sending our job to the shortest queue among the queried servers. JIQ, join idle queue, is an idleness differentiated policy. We are choosing where to assign the job based on knowledge about whether our servers are busy or idle, but not based on any information about the server speed, not based on any more detailed queue length information. SED, shortest expected delay, is a CLD policy. Now we're using server speed and queue length information. And the last specific policy that I want to put up here is what I'm calling ND for non-differentiated. And this is really a degenerate policy that just amounts to random assignment among the servers. This is kind of an uninteresting policy and definitely not a good idea. But I think it's a little bit interesting to put it up here to see where it fits with respect to the different assignment rule families that we consider. All right, so now that we've thought a little bit about querying, we've thought a little bit about assignment, we are now ready to think about what constitutes a dispatching policy. So a dispatching policy consists of a querying rule plus an assignment rule. We are going to choose some policy from our space of querying rules. These are parameterized by our P function. And we're going to choose some assignment rule that's parameterized by our alpha function. So once we've done this, once we've chosen a querying rule and an assignment rule, what we really end up with is a family of dispatching policies. So for example, what we'll write as IND CID is a family of policies parameterized by a P function that respects the rules of the IND querying rule family, and an alpha function that respects the rules of the CID assignment rule family. Within each of these possible families of dispatching policies, we are particularly interested in the best one, right? Our goal is to achieve low mean response time. So we're going to be particularly interested in the optimal policy within a family. So I'm going to use this asterisk to denote the optimal policy where we're jointly optimizing our P function and our alpha function to achieve the lowest possible mean response time. All right. So I next want to turn a little bit to our analytical approach. And what we were able to analyze are policies that use any general querying rule combined with a CID assignment rule. So an assignment rule that is using class information and idleness information. Our goal is to find our mean response time given a specific P and alpha. And we're going to need a few assumptions in order to help facilitate our analysis. We're going to let our number of servers go to infinity, and we're going to keep our fraction of servers within each class fixed. We will assume that the states of all servers of the same class evolve stochastically identically, And we're going to assume that all server states are independent. That's a fairly standard assumption when analyzing large-scale systems. So our main approach here is to tag a class I server and look at what happens when a new job arrives in steady state. We're going to ask ourselves, is the tag server queried? And if so, does it get assigned the job? All right, so I think we're now ready to jump into our analysis. And I'm going to start with a few preliminary observations. The first observation says that a tagged class I server has a different arrival rate when it's idle and when it's busy. And that's because we're using a CID assignment rule. And so we're allowed to make decisions based on whether this server is idle or busy. So I'm going to use this lambda I and lambda IB to denote the average arrival rate to an idle class I server and a busy class I server. Because we're making our decisions probabilistically, we're going to have a Poisson arrival process to this server, both when it's idle and when it's busy. Our second observation is that once the server is busy, it will behave like an MGI1 with arrival rate lambda busy. So this is nice because this allows us to learn all kinds of different things about what's going on with this server once it's busy. For example, we can determine the mean busy period duration via standard MG1 analysis. And from that, we can determine the fraction of time that a class I server is busy, rho I. And I've got this boxed in yellow here because this rho I is going to be one of the key quantities that we need for our mean response time analysis. So once we have our rho I, we're ready to move on to thinking about response time. The first thing that we'll do is we'll condition on a server's class. So what we're looking at here is the probability that a job actually ends up getting served on a class I server. So this numerator is the average arrival rate to a class I server divided by the arrival rate to the system. And then so we're conditioning on the server's class, we're going to multiply this by the mean response time at a class I server. We get this because, again, once the server is busy, it behaves like an MG1. And so this mean response time analysis just comes from standard MG1 analysis. And again, this can be for any work conserving scheduling policy. So we'll simplify this a little bit by dividing out by K. And now all that we need in order to finish our mean response time analysis, because we already have our rho I, we need our arrival rates, an arrival rate to an idle class I server and an arrival rate to a busy class I server. So this is our next step, finding our arrival rates. I'll just put up here as a reminder that our D vector is our query mix. And given our D vector, the probability that our tagged server is actually in the query is DI over KI. We're next going to need the rate at which the tag server is queried. So we know that if it's we know the probability that it's in the query is DI over KI. We're thinking about our arrival rate, so we're going to look at the rate at which we're queried. We have the overall arrival rate to the system, the probability of querying a particular mix, multiplied by the probability that the tag server is in the query given that mix. And we'll just simplify that a little bit by dividing by K. So now we know the rate at which the tag server is queried. What we need now is the probability that the job is actually sent to the tag server. Given our D vector, and because we're going to first think about our arrival rate to an idle server, given that the tag server is idle. So we're going to use this RI notation to denote this probability that the job is sent to our tag server when it's idle. And analogously, we'll use RB to denote what happens when the tag server is busy. Now, with these R notations in mind, we can now write the arrival rate to the tag server in terms of this RI when it's idle and in terms of RB when it's busy. So now all that's left for us is to find these R quantities, the probability that our job is sent to the tag server when it's idle and when it is busy. And that's our next step. This is our last step. We're almost there on the analysis. I'm going to define one more piece of notation. This is BI of D, and this is the probability that all faster queried servers are busy. This is an important quantity because remember, according to our pruning of our assignment rules, we are only actually going to send the job to an idle class I server if all of the faster queried servers are in fact busy. We're never going to send the job to a slower idle server over a faster idle server. So using our assumption that all of our servers all of our server states are independent, we get that this probability that all of the faster queried servers are busy is just the product over the faster classes, rho j to the dj. And now the job is assigned to a class I server with this alpha probability, where we're keeping track of I here is denoting that class I contains the fastest idle server, and D again is given our query mix. So now we're ready to put it all together. Our R function for an idle class I server starts with the probability that all faster queried servers are busy. This needs to happen in order to send our job to our tag server. We then need to decide to send the job to a class I server. This is our alpha probability. And then we need to think about the number of idle class I servers that were included in the query. So our last term is just going to say, all right, out of the DI servers, class I servers that were queried, how many of them were idle? And so that's what this combinatorial term at the end here is telling us. And that's our R function. All right, so we end up with a similar result for our RB function, the probability that we send our job to the tagged class I server when it is busy. And what we end up with is a system of equations. All of these yellow boxed quantities that we've seen throughout the analysis so far. Once we solve this system of equations, we can then go back to our conditional expression for our mean response time and plug everything in and get our results. So with our analysis, what we're now able to do is we're now able to look at some numerical results for CID assignment rules. So I'm going to show you some results for a particular system parameterization. We have S equals 3 server classes. We're querying 3 servers. And we're going to look at, as a function of lambda, a normalized mean response time. So what's on our y-axis is the mean response time under the best possible dispatching policy that uses CID assignment paired with a querying rule of interest. So different lines on this graph will correspond to different querying rules. And we're going to normalize that by the mean response time under the best possible gen CID policy that we can find. And so a value of 1 on this graph is going to mean that we're doing the best that we can do within CID assignment. Any value higher than 1 is bad. That means we are doing worse than the best achievable mean response time. The first policy that I'm going to put up here uses CID assignment in combination with balanced routing querying. So we have no free parameters in our querying decision. And as we can see here, this is not doing all that well for us. The lack of flexibility in our querying decisions is really hurting us. And in particular, when lambda is very low, there are going to be times when we never actually query a fast server. And we know that when lambda is very low, the best thing to do would be to throw out all but the very fastest servers. So balanced routing is not really doing the best possible possible work for us. Once we move to SRC, single random class, we're doing a lot better, particularly at low lambda. And that's because SRC is fixing the problem that we have with balanced routing at low lambda, where here we are actually discarding, we're only ever going to query the fastest server class. But we do a little bit worse when lambda is higher. So ideally, there'd be some way of achieving some sort of happy medium where we're getting the good performance of SRC at low lambda and the slightly better performance of balanced routing at high lambda. And it turns out we can achieve that using our IID querying rules, again, in combination with CID assignment. Now we're doing almost as well as gen, as the best possible dispatching policies that use CID. And we can do even a little bit better using IND querying. So you might be wondering, why does this matter? Why don't we just optimize within gen and find the best thing that we can do with CID assignment? And the answer here is that for each of these restrictions on the gen querying rules, we can set up a slightly different optimization problem. So the optimization problem for IND, because it's a restriction of gen, can be set up in a little bit of a different way that ends up actually being much more efficient to optimize. So it's really powerful for us that we're able to get almost as good performance out of IND as we can considering the entire gen family when we're able to solve that optimization problem for IND much more quickly. So this is all good and well, but so far the numerical results that we have been looking at have only been for CID assignment. We're using information about whether servers are busy or idle, but we're not using more detailed queue length information. Where we started this discussion was with policies like JSQ and SED that use the full queue length information. So I'm going to squish all of our results up on this axis and extend our y-axis down to below 1. And this will allow us to look at what happens when we consider CLD assignment rules. So the next line that I'm going to put on this graph is the best that we can do within the gen CLD class. This is using any possible querying rule jointly optimized with any possible CLD assignment rule. And we can see now that we're actually doing quite a bit better. We're getting much better performance when we're using queue length information, unsurprisingly. Now, the problem here is that CLD policies are typically much harder to analyze than CID policies. And so optimizing CLD policies is a lot more challenging. It's not as easy to find those really good policies under CLD. So we wanted to come up with some heuristics that will allow us to find good CLD-based dispatching policies without having to go to the trouble of actually analyzing the full space of CLD policies. So if we go back to this idea that a dispatching policy consists of a querying rule and an assignment rule, one way that we can get around having to do a lot of optimization is by using off-the-shelf pre-parameterized CLD assignment rules. So we can use specific assignment rules such as JIQ and SED, and then we can pair these specific length-based assignment rules with specific querying rules. We can pair these assignment rules with querying rules like balanced routing that don't require any optimization because they come prepackaged with their parameters. We can pair these with querying rules that yield tractable analysis, like single random class. When we combine single random class with JSQ, for example, our system reduces to a homogeneous JSQD dispatching system, which we know how to analyze. And we can also pair these specific CLD assignment rules with our optimized CID-based querying rules. What happens when we do this, when we use this sort of mix and match approach to defining CLD-based dispatching policies, I'm going to get rid of our CID results here. When we start with balanced routing, we're not actually doing all that well. Unsurprisingly, balanced routing has poor performance at low lambda, again, because sometimes we're not including our fast servers. But our other options actually end up doing quite well. We're doing very, very well at low lambda. We're only using our fastest server classes. And we're really getting almost as good as the performance under Gen CLD under a lot of these other policies. What's going on here is that all of our policies have similar performance at low lambda because here they're all succeeding at only using the fastest servers. At higher lambda, we start to see a little bit of a gap between the JSQ-based policies and the SED-based policies. And this is happening because when lambda is very, very high, all of these policies end up using pretty much the same querying rules in order to maintain the stability of the system. We have to ensure that every class gets queried often enough if we want to keep our system stable as load increases. And so it really turns out that assignment becomes the key factor driving the performance of our different dispatching policies when lambda is very, very high. So the idea here, the goal in this heuristic picture is just to kind of illustrate that we can get a lot more power out of using CLD-based assignment rather than CID-based assignment. But the value of our analysis of CID policies is that it allows us to identify really good querying rules to use in combination with CLD assignment rules. So I'm going to wrap up here. Again, what we've done in this work is we've thought about dispatching in heterogeneous systems. We've broken up our dispatching policy into two pieces, a querying rule that tells us which D servers to query, and an assignment rule that tells us where to send our job among our D queried servers. We analyzed within this framework dispatching policies that use CID assignment. We thought a little bit about how we can leverage that analysis to design CLD policies, class and length differentiated policies that achieve good performance. We have a lot of ongoing work in this space. Some of our recent work is focused on trying to actually develop some new analysis for CLD-based policies and trying to use this kind of framework in other settings to design other kinds of dispatching policies. I have found this to be a really interesting direction of work to think about. I hope that you have too, and I'm happy to take any questions. Thanks very much.
I have a few questions, if I may start. So I have a question about the very first plot that you showed, Christy, where you had like numerical experiments of various algorithms, and then it looks like JSQ is going down with lambda. So I found it very surprising.
Yeah, it's a really weird result. This was really surprising to us too the first time that we saw it. And what's happening here is that this actually has to do with the extent to which the fast servers are being used. So we're doing uniform querying of our servers. And so when lambda is really, really low, we're going to query our fast servers and our slow servers kind of with equal probability. And then because all of our servers are idle when lambda is really low, there's nothing that tells us it's better to use a fast server than a slow server. And so we're sort of sending, I think you just got it. So we're sending jobs to fast and slow servers sort of in proportion to the number of servers that are fast and slow. As lambda starts to increase, if you send the same number of jobs to fast and slow servers, the fast servers are going to work through their jobs faster. And so they're going to end up having the shorter queues. And now we're actually end up using the fast servers a little bit more often than the slow servers. I'm glad that you asked that question, because that was definitely one of the weirder things that we saw when we started working on this, and it was kind of fun to think through what was going on there.
Cool. My second question is about the CLD stuff that you talked at the very end. So you walked us through the calculations you did to get to find the optimal CID policy. Did you repeat the same calculations in the CLD setting in order to find the best CLD policy in order to like eventually make this plot?
In order to make this plot in the end.
The purple.
Yeah, so a lot of our ongoing work is about doing the analysis of the CLD policies. And I think that we would probably have to ask Jazim exactly where this line came from. Jazim Abdul-Jalil is one of the graduate students working on this work, and I know that he's the one who actually produced this plot. I don't know off the top of my head whether this line came from some of our more recent work on analyzing CLD, or whether it came from like a grid search kind of optimization that he might have done to try to find the optimal policy. I think that we are at a point now in our work where we can do some of this analysis of CLD. I just don't remember exactly where this particular graph was generated.
I'll ask one more question before others get a chance to talk, I guess. So if you go to the prod just before this, where you focus on CID alone, so you showed how when you go from IID to IND, you have improvement. Is there an intuitive explanation for why that is the case?
So I think really the intuitive explanation is just that IID is a strict subset of IND. And so there are just some policies. If we go back to
sure.
If we go back to this picture.
Part, but like even when you defined it, I didn't see. So essentially what you're saying is that all these D queries are not using the same distribution. You should change the distribution with respect to as the index increases to D.
Right, right.
So do you know how that has to be changed based on the structure of the optimal policy, for instance?
I think I don't have very good intuition for how that has to change. And in particular, what I want to point out here, if I can find this is not the right slide. Let me see if I can find the graph again that we were just looking at. This one, maybe the one right
the
before.
one just before
this one. We can see that we're doing the same in this low lambda region. And then we're doing the same in this middle region too. And then it's only when lambda's, moderate to high that that IND is doing better. I don't think I have really good intuition for why that is. I think it's just that when lambda gets really, really high, maybe here's what it is. IND is going to be constrained to doing essentially the balanced routing querying, where we're going to have to query the server classes in proportion to their speeds in order to make sure that we're hitting everybody often enough for stability. And IND just gets a little bit more flexibility to adjust how we do that, how we make sure that we hit all of the servers often enough. And I just think that little additional bit of flexibility at high lambda is probably helping us out. But I think beyond that, I don't know enough about what the specific policies look like to give you a better answer.
Okay, thanks.
Hey, Christy. Yeah.
Go ahead.
Hey, Christy.
Hi.
Great talk. First of all, as a lifelong scheduling person, I really liked all your Venn diagrams. Those were really nice. Just have a couple questions. First, can you say a little bit about the like in the CID case, those optimization problems? You mentioned a little bit about this in terms of making things easier to solve versus like a gen policy. So I guess these things, they must be nonlinear, non-convex. I mean, can you just say a little bit about like how hard these problems are and the difference that you mentioned?
Yeah, I'm gonna pull up our paper because that information doesn't live in my head, but it does live in our paper on this work. And so yeah, so I think they are nonlinear, they're non-convex. This actually makes them very hard to optimize at all. And one of the things that has been interesting to us is that when we optimize, we're using a particular optimization package, IPOpt. And so in fact, what we're presenting as an optimal solution is definitely locally optimal. And as far as we can tell, probably globally optimal, but because these are such challenging problems to solve, there's a little bit of a caveat to what we mean precisely when we say that something is an optimal solution. I think that maybe I'll leave the answer to the question at that for now, and I encourage you to go take a look at the paper. I can send you a copy of the paper if you want to dig more into what the optimization problems actually look like. Yeah,
just curious on. I like the connections with optimization, and then I think you had mentioned mean field analysis at the beginning of the talk, but if I understood up to the CID part up to slide 20, well, roughly here, I mean, all of that is at least for Poisson arrivals, this is exact, right? I mean, there's no approximation there. Is that correct?
So the place where we're sort of making an approximation is that we have these two assumptions. One is that all of our servers evolve stochastically identically. And the other is, and I think that assumption is probably accurate once you take that our policies are symmetric. But the other is that we're assuming that our server states are independent in the limit as the number of servers goes to infinity. And that's really where the mean field result comes in, because that will not hold if we're dealing with a much smaller system.
Okay.
Imagine they're in like a join the shortest queue kind of policy. The queue lengths really are quite dependent on each other. So that's where the approximation comes in.
Okay, I think I missed that subtlety, but thanks for the clarification. Thanks.
Other questions?
I have a follow-up question to John's question. So
Sure.
I got the asymptotic independence, but I didn't realize that they're assuming all servers evolve like stochastically identically, what does it mean? Because the servers have different speeds, right? So are you
So
assuming that
all servers of the same class.
same class? Okay.
Yeah, same class. Yeah, of course, that's an important phrase in there.
Right. So you're indeed assuming that the distribution of queue lengths across classes is different. It's identical for all servers in the same class. It's different across classes, and they're all independent of each other.
Yes, exactly.
Okay, cool.
And I'll add also that we have done work to validate the analysis via simulation, and we've seen that this matches up really exactly to what we're getting from the simulation. So we do believe that those assumptions are indeed valid for this particular setting.
So how easy or hard do you think is it to justify these assumptions? Because asymptotic independence and mean field limits is known and like fair amount of generality, right? So is it possible to plug and play any of those results, or are there challenges in studying the heterogeneous setting?
So I would guess that this is provable. I am not someone who has done a lot of work on proving asymptotic optimality results. And honestly, that is in part because that just tends to be a flavor of work in this kind of problem that doesn't feel as compelling to me. And I know there are lots of folks, some of whom are in the Zoom today who have a lot of expertise in that space. And any one of them might be able to give you a more informed answer than I can about how likely it is. My guess is that it can be done. And my guess is that we have colleagues who are here who could probably do it. I think it's usually a little bit harder to do when there's heterogeneity involved, but I don't think there's anything quite so complicated going on in the kinds of systems that we're dealing with that it should, really be not within reach.
So I have a question about when you solve for the optimal policy within each class, do you need to know the arrival rate information, or you only need to know the service rate information?
No, so the arrival rate is part of the optimization problem. And that's what allows us to end up with very different kinds of policies at different lambdas. So we end up at really, really low lambdas with all of these policies that throw out all but the fastest servers. And then of course we need the faster servers when lambda is higher. And so the lambda absolutely is part of the optimization problem.
I see. So when you think about like the potential implementation of these type of policies in practice, I guess the arrival rate are probably going to change over time. So is there an intuitive or heuristic way of adjusting for the different arrival rate, adapt to different arrival rate with real-time information?
Yeah, so this is a good question. And I think that the answer is probably just that you would want to periodically rerun the optimization problem. And, as you're measuring your arrival rate in real time, once you sort of reach a point where it's changed, beyond some epsilon, you would rerun the optimization problem. When I say that some of these optimization problems take a long time to run, we're not talking days here, we're talking, on a much smaller order. So it's feasible to rerun. If your arrival rate were changing really, really rapidly, I'm not sure it would be feasible to rerun, but then if your arrival rate is changing really, really rapidly, it kind of just looks like you're experiencing, a different kind of average arrival rate.
I see. I guess among the classes you talked about, any class that are relatively robust to different arrival rate information, or the policy really changes a lot depending on what the arrival rate looks like?
So I think the policies tend to change quite a bit. And really this comes back to thinking about those two extreme points. Really low lambda, you only want the fast servers. Really high lambda, you kind of have to sample in proportion to the speeds, or your stability is going to go away. So things definitely do change between those endpoints. I think they tend to change fairly smoothly. So you'll have places where the policy changes. It's not just all over the place all the time. So there's maybe something that can be done to kind of ensure that you don't have to change your policy too often.
I see. Great. Thank you. All right. I guess if there's no further questions, then let's thank the speaker again. Thank you, Christy, for the very interesting and excellent talk.
Thanks so much for inviting me to be here, and thank you all for coming, and please feel free to shoot me an email if you have other questions.
All right.
Yes, Christy. Bye.